Hello dear students, today we will discuss the next point in quantum free electron theory, that is density of states. So what do you mean by this density of states? The density of states is defined as a mathematical function that gives us the possible energy quantum states per unit volume, per unit energy of the electron inside a solid metal. Now in the figure you can see this is the energy level diagram. So this is the Fermi level. Now the energy range is in between E to E plus dE at 0 Kelvin. So this Fermi energy or the Fermi level is the topmost collection of electrons at 0 Kelvin, and the corresponding energy is called as Fermi energy. Now below this Fermi energy all the energy levels are filled. Above this Fermi energy all the energy levels are vacant. Now the density of states is nothing but it is the energy levels or the density of the states between this energy level and this energy level. A small unit energy, and we are going to see how many number of density of states are there. That is the reason we will define it as the possible energy quantum states per unit volume, per unit volume, per unit energy. This is the per unit energy from this energy state to this energy state, and we will see how many number of density of states are present inside a solid metal. So this is how we will define the density of states. So here the number of electrons per unit volume having energies between E1 and E2 is given by. So the number of electrons per unit volume having energy is between E1 and E2 is given by N of EdE is equals to rho of EdE into F of E, where F of E we have already discussed it as Fermi factor. Okay, here rho of E into dE is called as the density of states. So if you want to find out the total number of electrons per unit volume, then you need to multiply the density of states into Fermi factor. So that is the reason the expression for density of states can be given by rho of E dE is equals to 8 root 2 pi m raised to 3 by 2 divided by h cube e raised to 1 by 2 into dE. So this is how we will define the density of states. Now we will go for a derivation, which is expression for Fermi energy at 0 Kelvin. So here we already defined the Fermi energy, the topmost collection of electrons at 0 Kelvin is called as Fermi level, corresponding energy is called as Fermi energy. Below the Fermi energy or the Fermi level all the energy levels are filled with the electrons, and the energy levels above Fermi energy are vacant. Now the number of electrons per unit volume having energies between E and E plus dE is given by. So here our energy range is from E to E plus dE. In this energy range, how many number of electrons are present per unit volume can be given by N of EdE is equals to rho of EdE into F of E. Rho of E is the density of states that we have discussed just now. Rho of E is the Fermi factor, which is a probability of getting an electron. So rho of E can be given as this, F of E can be given like this. These two already we have discussed. So now at 0 Kelvin only energy levels up to Fermi energy are filled. So at 0 Kelvin only the energy levels below Fermi energy are filled, that is up to Fermi energy are filled. Above Fermi energy they will be vacant. Therefore at 0 Kelvin only energy levels up to Fermi energy are filled. Therefore F of E probability function will be 1 for energy levels less than Fermi energy. Now therefore the number of electrons per unit volume is given by number of electrons per unit volume can be given by this expression. N is equals to integration from 0 to Fermi energy EF rho of E dE is equals to, since f of E is equals to 1, it will become only rho of E into dE. This is equals to integration from 0 to EF rho of E equation. This we are going to substitute here. So this expression we are going to integrate. So in this we will take out the common terms, 8 root 2 pi m raised to 3 by 2 divided by h cube, and we will integrate only e raised to 1 by 2 from limit 0 to EF into dE. So here when we integrate it, e raised to 1 by 2, we will be getting 2 by 3 EF raised to 3 by 2. This E is going to be EF because our limit is Fermi energy. Then we want the expression for Fermi energy. So we will just keep this term and remaining all the terms we will send it on the other side. So we will be having EF raised to 3 by 2 is equals to this 3 h cube, will be sending it on this side, 3 h cube into N divided by 8 into 2, 16 pi raised to into root 2 m raised to 3 by 2, right? So this is going to be the expression EF, but we want only EF. This is EF raised to 3 by 2. This we will take it as 2 by 3. So when you simplify this term, we will just take 1 divided by 16 root 2 raised to 2 by 3, 1 divided by 16 root 2, h cube divided by m raised to 3 by 2, h cube divided by m raised to 3 by 2 raised to 2 by 3, and 3n divided by pi raised to 2 by 3. So when you simplify this term, you'll be getting it as 1 divided by 8. When you simplify this term, you'll be getting it as h square divided by m, and when you simplify this term, it will remain as it is, 3n divided by pi raised to 2 by 3. Now rearranging these terms, EF is equals to h square divided by 8m 3 by pi raised to 2 by 3 into n raised to 2 by 3, which means your Fermi energy is dependent on the Planck's constant, mass of an electron, and the number of free electrons, right? So if we substitute all these constant values and simplify, we will get this value as 5.85 into 10 to the power of minus 38. So the Fermi energy expression can also be written as 5.85 into 10 to the power of minus 38 into n raised to 2 by 3 in terms of joules. So this is the expression for Fermi energy at 0 Kelvin. Thank you.